Welcome. We are going to look at the square root function, and that is what's shown right here. In fact, I'll put it in yellow. This one's called the parent function because it's the most basic thing in this group of functions. We've looked at a number of functions already, especially linear equations, which are straight lines, and other things like parabolas or quadratics. And this one in particular, the square root is a certain type of function. So we're going to start with the fact, let's see, I'm going to write this over here in order to show something about it. The x inside it. Well, there's limitations to what x's you can have because of the fact that you cannot have the square root of a negative number. That makes it imaginary, which we can work with in math, but not when it comes to graphing or getting real numbers from the square root. So that means that the number that's here must be greater than, let's say, greater than or equal to 0. Because 0 itself, the square root of 0 is 0, so 0 is a good number. So what we're going to do, in fact, we're going to use the concept that whatever is in here, this x, in this case just x, must be greater than or equal to 0. That means that 0 itself is the first number that it can use. So we'll put we'll put a 0 there. And then we will do y equals square root of 0, and that equals 0, and therefore the matching number with it is 0. Now we do it for the number 1. Let's go up 1. Y equals square root of 1. The square root of 1 is simply the number 1. Now, if we put 2 in, y equals square root of 2, we get a number that's approximately 1.41 and then some other things after it. You could do that. However, it's a little easier to graph things on the graph if you can get numbers that are whole numbers or actual integers, negative or positive. So instead, thinking of the fact that perfect squares will give you a nice single number that's not a decimal over here as the answer, we can instead, for our next one, use the number 4. We'll go up to 4 because the square root of 4 is equal to 2. Okay, so now, let's see, that brings us to 2. And the next perfect square is the number 9, which gives us a 3. That's all I can use on here if I'm going to go by 1. So let's graph all of these now as points. 0, 0, 1, 1, 2, 3, 4, and 2, and 9 and 3. And let's make this 0, 0 a little more really on 0, 0. Notice that the graph goes like this curve. So there's some characteristics of this kind of graph. One of them is that you can't use anything less than, not necessarily 0, but the number that would make 0 under the square root. Also, the look of it is always going to be this kind of a curve. It might go other ways, like it could go down, or it could go way up faster. It could start in another place. All those other things are true. However, but actually that no matter where it is or what it looks like, it still has this kind of curve. If it doesn't, it's not a square root one, almost certainly. Okay, we've graphed this one by using this table of values. Let's do it down here. And the first thing we need to notice is that underneath it here, 0 would not work because 0 would give us a negative number. 1 would not work because 1 minus 3 is negative 2, negative number. We can't use it. 4 would work, but instead, let's do the method that I pointed out. Let's take what's underneath. This is called a radicand. Let's take out underneath it, the radical sign, and make it greater than or equal to 0. And then we're going to solve for x. So 3 is our starting point. So we'll put a 3 here. And so y is equal to square root of 3 minus 3 plus 1. Put a little equals there. So that's 0 plus 1, so we get a 1. And now we'll do it with the next number up. Almost certainly, not always, but most of the time, a 1, whatever the next number up from it would work well. So that's 4 minus 3 plus 1. That's square root of 1 plus 1. That's 1 plus 1. That's a 2. And now I have to get a little more creative. I want this to become the number 9. So I think, what do I have to put in there? Let's see. Oh, no. Let's see. 4 to get 2. I guess I've done square root of 1. Let's do square root of 4. So if I need a 4, I would put a 5, 6, 7. 7 minus 3 would work. So let's try it with a 7. Y is equal to square root of 7 minus 3 plus 1. And that's y is equal to square root of 4 plus 1. That's 2. So 2 plus 1 is the number 3. And now then we'll think the same thing. If I want it to be a 9, I would need to put a 12 there. 12 minus 3. So this part of it would become square root of 9, or 3. 3 plus 1 is 4, so a 12 and 4. Well, we can't graph the 12 on here easily unless we don't go by ones, but let's graph the first 3. So 3, 1, 4, 2, 7, 3. 3 and 1. 4 and 2. 7, 5, 6, 7, and 3. And if we did go a little further, we could go to 12 and 4. So it has a starting point. Whoops, let's get this back to where it should look. Okay, it has a starting point. That's one characteristic. So here's the starting point. And it goes in a slightly gentle curve past that. That's the other characteristic. And that's how it's graphed. It's no longer at 0, 0, but because the inside of it moves it, in fact, it's negative. You'd think it should be a positive to go towards the positive, but it's not. It's an opposite sign thing. The reason for that is because in reality, this is called x minus negative h. So if that's a negative, then this one has to actually be a plus here in order to get that to be a negative. And if it were a plus 3, that would mean it was a minus minus, which means we'd go the other direction. But it's not, so we'll keep to this one. And then this plus really does mean going up. That's called a vertical movement for it. There's other vocabulary words for it, but we're going vertically with the 1 and horizontally with what's inside here, in this case, a 3 to the right. Okay, now let's go back and look at something. Let's see, I'll come down here for a different one, but because now I'm going to talk about the domain and range part of this. Okay, for the domain, we are talking the x values that are, let's go like that. The domain are the x values that are actually part of this graph. And the range are the y values. So what I'm going to do here is I'll use these. Yellow, I'll show what the x's are, and in green, I'll show what the y's are. So in yellow, right now you can tell, in fact, this shows you some of them, but it's actually, since we have a starting point at 0, 0, we're using all of the x's all the way going out to infinity in order to have the points that are on here. And for the y values, we're starting at 0 and we're going up because sooner or later this arrow is going to get up higher and higher and higher, and it'll go up. It just goes up very slowly. So all of the y's and all of the x's that are positive are in the domain. Now we can show that in a couple of different ways. I'm going to put the domain, and I'm going to say is in this bracket form, are the x's that are greater than or equal to 0. And there's other methods. In integrated 3, we will go over a different method called the interval notation method, but in this case, we'll stick with this one. And the range, let's use yellow for that now. The green are, did not mean for those to disappear. Green are the y values. So we'll say the range are the y's that are greater than or equal to 0. And so that's the domain and the range. It's just saying which x's are acceptable in this graph and which y values are acceptable in this graph. Let's look at the next one now. Now we see it a little differently. We have the number 3 as our starting point, which is why he's doing this was important, and all the numbers greater than that 3 are good. And for the y values, the first y that we use is 1, and then we go up from there. So notice what I'm doing here is I'm matching the y and the x from that first point. So the domain, I'll put it right underneath here, the domain, or D, is all the x's that are greater than or equal to 3. Not 0 this time, but 3. And the range, which I'll write out, are the y values that are greater than or equal to 1 in this case. So there, just matching colors go with it. Notice something about this. Notice that we have 3 for the x's, and then up here we have -3 inside there. So it's just the opposite number of that. And for the y's, it's a 1 for the first one, and we have that already in the equation. Let's use that concept on this next thing. I have a couple of, well, actually, we'll come back to it. We'll do a couple of other examples here. So, yeah, we've done that one. Let's do this one. Well, right here, what I see, we have to take this part. Let's take the square out. X plus 3 is greater than or equal to 0. Let's subtract 3. X greater than or equal to -3. So put a -3 in here. And so -3 put in this spot would give you a square root of 0, which is perfectly good. Then what we get, let's write that out, we get 2, square root of 0 is 0, minus 1. Well, since that's 0, we get a -1. Now let's do it for not -4, because if we put a -4 in here, we'd get a negative number. So instead, what we're going to do is we're going to put in a -2. So that if I do y equals 2, square root, not parentheses, square root of -2 plus 3, and then -1, the -2 plus 3 gives us a square root of 1. And 2 times 1 is 2, minus 1, 2 minus 1 is 1. There, so we've got 1s here, a -1 and a 1. Oh, let's do it for the next number up, except I would like if this would be a 4. So if I want this to be a 4, I need a -1 in that spot. No, wait a minute, is it 4? No, I need a positive 1. 1 plus 3 would make 4. So that means I'm going to jump up here to a positive 1, and I'm going to do y equals 2. Square root of 1 plus 3 minus 1. And that's 2 square root of 4, which is times 2. 2 times 2 is 4. 4 minus 1 is equal to 3. So we've got a 3. I can go up a little further again. I can do at least one more easily here, because now I was able to get 4. Now what if I wanted 9? If I wanted a square root of 9, because that would be equal to 3, I would have to make that x into a 6. So let's put 6 here, and then let's do y equals to square root of 6 plus 3 minus 1. Well, square root of 6 plus 3 is square root of 9. Square root of 9 is a 3. 2 times 3 is 6. 6 minus 1 is 5. Okay, now let's graph those. That should be enough to get our curve that we need to see. And we start with -3 and -1 right here. And then -2 and +1. 1 and +3. 6 and 5. Oh, did I miss a 4 here? Yeah, no, it's right. It's a 5. It should be. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Ah, and that confirms. Look at the curve that I get. That's about the kind of curve that the original one was. This is where, if I can draw it out right, this is the parent function curve. So what happens here is it starts at a different place, and it goes up a little bit faster. That's what this 2 does over here. The multiplier of the 2 makes it everything go up faster, essentially double. And the plus 3 moved it to the left 3 places, and the minus 1 moved it all down 1. So we went over 3 and down 1, and then we used the numbers here to tell us how high we should go. We let the table of values show us that. All right, now the domain and range. In this case, the domain starts with that -3 and goes forever. So underneath this, I'm going to put domain are all the x's that are greater than or equal to -3. So negative's just fine for this. And the range are all the y's greater than or equal to 1. So we go and see what are the x's and the y's that we start with, because all the y's are here. Those are the only y's that this graph actually uses, so they can't be less than the number 1, or -1, I should say. It's supposed to be a -1, so let's make it -1. So this was the domain. Get it so that, oh, I'm sorry, these things disappearing. I'll go slower and see if it'll keep my yellow on it. Good. And now for the green one, that seems to go on a little easier. Okay. So range in yellow, domain in green, and this one just showing that in this sense, the concept is the domain are all the x's from a starting point, and the range are all the y values from a starting point. Okay, now let's take a look at another one, and this one has a twist to it. Look at that twist of negative. Okay, now that is going to change where it goes. However, it won't change the starting point, which is still this, x minus 2 greater than or equal to 0. So I'm going to add 2, so x is greater than or equal to 2. And now let's figure that out. -5 square root 2 minus 2 we just know is 0 plus 7. -5 times 0 is 0 plus 7. So we get a 7. So we're going to have 2 and 7 as our first starting point. I'll go up to it now and put a point there. I think I'll put that one in blue, though. That's the starting point. Now, interesting thing is that our next number we might want to do is a 3. So we can do that, and we're going to see what happens with the number. It won't get larger with 7. So I can't go to 1, because if I put a 1 in here, I'll get a negative, but I can put a 3 in here. So I get -5, 3 minus 2 plus 7. That's -5. Well, square root of 1 is 1. So 7 take away 5. Wow, that's a big difference, is 2. So 3 and 2. So -5 plus 7. Interesting. Now, if I go to 4, that gives me a square root of 2. 5 of 2, I don't want that. 5 gives me a 3. 6 gives me a 4. So let's do it with a 6. So -5, y equals -5 square root of 6 minus 2 plus 7. -5 square root of 4 plus 7. That's why we can get a 2 here. So that's -10 plus 7. That gives us a -3 here. Okay, the next number I'd want to try to get to if I were going for perfect squares, because I've just used that a 4. The 6 gives us a 4 inside there. Okay, so I would need an 11 to get a 9. 11 minus 2 would be 9. Well, we're close on the graph with an 11, so let's go ahead and calculate that one. Y equals -5 square root of 11 minus 2 plus 7 equals -5. 11 minus 2 is 9. Square root of 9 is a 3. So that's -15 plus 7, which is a -8. And that was for the number 11. Okay, now watch what happens when we graph these. 3 and 2, and 6 and -3. And 11 is just 1 off the graph, so I'll just go extend it a little bit. And that's down at -8. So we have a curve like this. I can't draw it very well. Do a little better this way. That's not so good either. So that is very different in a way from these others, except it does have the curve. There are two things happening here. One is the negative that flips it upside down, and the other one is the 5 that stretches it way out. And if that had been up, it would have been like, if this had been a 5 instead of a 2, it would have been like this. And so that concept of then flipping it plays. So it actually does make sense based upon the idea that the negative would flip it over the x-axis in a way. Or no, it's not over the x-axis. What it is instead of the x-axis, wherever that first point is, that horizontal line becomes the axis for this. So if that had been a plus 5, we would have been going up like this. Actually, the negative would have changed the numbers. So it actually would have been in a very different place. So we just won't worry about that. What we will say is that if you do the numbers here correctly for every x getting the correct y, you would get the right points to put in so you can get that sort of gentle curve with it. Now, domain and range. So the domain looks like it's this x all the way over, which is 2. So the domain are x's, let's make that a better bracket, all the x's that are greater than or equal to 2. And the range are all the y's, but this time it's starting at 7 and going down. Notice that in this case, we aren't able to actually count that to recognize. We know that we're starting at a plus 7. But we can't count on that to know if it's greater than or if it's less than, except that this tells us. So in the ones above it, we have a plus in front of it. That tells us it's going to be greater than or equal for the range. And this one, there's a plus in front of it, so it's greater than or equal for the range. In this one, of course, there's nothing after it, but because it's positive in front, simply because there's no negative, we know that the range will be greater than or equal. Well, when we come down here, when you're dealing with a negative at the beginning, that means that the range will be less than or equal to, not greater than. And the reason is because what you see physically here with this, all the y values are below. So it's y's less than or equal to the 7. So the number that comes afterwards is still the right number, this 7. And the number inside is still the opposite of that because it was minus 2 and we put a plus 2. So this is the domain, and this is the range. I think what we'll do is circle that one so we can see that those two numbers are still there, but this is the big difference for it here. Okay. Now, next thing, let's talk about the idea of what transformations do. Transformations shown in this. There are 4 things: that negative, that 5, the plus 2, and the plus 3. Okay, so what we're going to look at is what happens with each of those, and basically let's calculate. Well, it's not really calculate. In this case, it's simply nothing more than placement. Okay, so let's start with what the negative stands for, with the 5, with the plus 2, and with the plus 3. So based on its placement, the negative means that it is reflected. I don't like how I wrote that. So reflected, there, now it looks better. Reflected over, or on is sometimes used, but I think over makes more sense, over the axis. And the axis is from first point. Oh, get my program working right here. go back from that. And we finish the word point there. The 5 means that it's either a stretch or a shrink of it. In this case, it's making it much larger, so it's stretching it. Stretching by a factor of 5. Now, it doesn't really matter much, but I'm going to change the word here to stretch just to go along with past tense. Since I said reflected here, I'm going to do stretched here. And then I'm going to do translated. So first for the 5, it's stretched, and by that much, by multiplying by 5. So we have reflected and we have stretched. Now we have translated. Two units. We haven't decided if it's inches or millimeter or something else on that, so we'll just say units. 2 units. Now, because it's plus, that means it will be going to the left. To the left. So plus means going that way, and minus means going that way on it. Left or right. So that's left and that's right. Now the plus 3 at the end of it is also a translation. Translated 3 units up. Minus would be down. And so we have 2 of them that are translated, but one is going horizontal and one's going vertical. So it's called a horizontal translation and a vertical translation. And then it's reflected and stretched. These are all transformations. So they transform, changing the parent function into a different one. You don't have to have all 4 of these. You might have just one of them. Or 2 of them. You don't have to have all of these in order to do it. Or you might have none and it'll be the parent function. Okay, now the opposite here, what we just did in this is we took out all these things from the equation. Now on this one, we have to put all these things into the equation. And here's the basic equation. Y equals a possible plus or minus, and then what we would call a, which is that multiplier, and then the square root of x minus h plus k. H is the horizontal change, and k is the vertical change, and a is the stretch or shrink. And the negative is if it is being reflected. Reflected. So it can be reflected, stretched, or shrunk. Okay, let me also write that word so it looks better. Shrink. And then we have a horizontal change or we have a vertical change. So what we do see up here is translated 4 units right, 5 units down, reflects over the x-axis, and contracts or shrinks by a factor of 1/5. So that's another way that you could say shrink, is you could say contracts. Let's write that a little bit neater. Contracts. Now, I'm still not sure I got that A clearly in there, so yes, I'm going to fix it again. Now, what we're going to do is put all those into this, so we're going to say y is equal to, it does have a reflection, so we'll put the minus. It does have a shrink or contracting, or making it smaller, which is 1/3, and then the square root, and then it's x, so we have to think. It's going 4 units to the right, so that means it's a negative. If it was going the other way, it'd be plus. So it's going to be minus 4, and then this one says it's 5 units down, so it'd be minus 5. So that includes all 4 things in it. It includes the minus, it includes the 1/3, just don't want that to disappear, the negative 4, Let's get that one back. And the -5. Okay, I'm done with using the yellow pen. Oh, the highlighter part. So these two kinds of problems are exact opposites of each other. Now to come back for a moment, let's review. Everyone's used to XY tables. What people have to get used to here is doing the finding of the first term. Let's use blue for it. Finding that, in this case, by making it greater than or equal to 0, like it was done here, to do this to find out what that first x is. So that's the first most important thing people need to pay attention to on doing the XY table. Second, knowing how to handle finding the domain and the range. Visually, on one hand, it's really pretty easy. You just have to remember that it's all the x's that are being used in the graph and all the y's that are being used in the graph, not the ones that are not used. Because this type has a starting point, you can't use the ones before that starting point. And so paying attention to and understanding domain and range is important for analyzing like where it is possible to have points for this graph. It's only possible for x's that are greater than or equal to 3 on this one, and y's with y's that are greater than or equal to 1. So those are the only ones possible. We did that for each one of these. Okay. So you see 4 examples of domain and range, so you could find those if you needed to. And then, of course, knowing the transformations. The only difficult thing here really is remembering where they're placed and remembering whether it's minus or plus for going to the right or the left. So focus on and remember that, and you'll be able to get these right all the time. Okay, I hope this was helpful. Thank you for watching and listening.